Hello, today we'll be studying the introduction to quadratics. We've already talked about a little bit about quadratics in class. Today we're going to get to what they look like and just some important bits of information about them. We'll start with the equation for the quadratic function. It's a little different than what you've seen before. Looks a lot more complex, a lot fancier. It's written, a quadratic equation is going to be written in the form y equals ax squared plus bx plus c. And what that does is that creates a different graph. With a regular linear equation, you get a line. With this, you get what's called a parabola. A parabola is this U-shaped graph. It either shoots up like this or it opens down, but it will not open to the sides because this still is a function. And if we had a parabola that went on its side, again, that wouldn't match our linear our vertical line test. But where one like this, of course, we do a vertical line test, it works. So this is still a function, but this is one formed by a different type of equation, which is what we'll talk about next. We've been studying linear. Linear is y equals mx plus b. And as we just said, quadratic is ax squared plus bx plus c. The biggest difference you should notice right off is that a linear has just an x and a quadratic has an x squared. Doesn't seem like that big a deal, but if you were to think about this x, if it had a coefficient of, say, 3, then whatever we put in place of that x, say 1, 2, 3, 4, we would have 3 times 1 is 3, 3 times 2 is 6, 3 times 3 is 9, 3 times 4 is 12. And we get solutions of 3, 6, 9, 12, and of course we could go on 15, 18, 21, 24, and so forth. We have a nice linear progression, a nice steady progression. It's the same jump each time. We do the same thing with a 3x squared, or put the x squared, put a 3 in front of it, so now we have 3x squared. We put the same numbers in, 1, 2, 3, 4. Okay, so we put a 1 in, that's going to be 3 times 1 squared, so 3 times 1 is 3. We put a 2 in, so now it's 3 times 2 squared, which is 4, so 3 times 4 is 12. So now we've jumped from 3 to 12. We put a 3 squared in, that's 9. 3 times 9 is 27. So now we've gone 3, 12, 27. And if we put a 4 squared in, that's 16. And 3 times 16 is going to jump us up to 48. So we're making big jumps each time, and they're getting bigger each time. It's not constant. And that's what creates this difference. We have on the right a linear equation, or linear graph, creates a nice line. We have on the right a parabola formed by a quadratic. We compare them together, and you can see that even though they are different, they do have some similarities. In this case, the two equations that we have here, the one on the right is actually, or the one in blue I should say, is actually y equals 3x plus 4. The one in red is actually y equals x squared plus 3x plus 4. So you can see they do have some similarities here. Now, when we look at these parabolas, we'll get into what creates them and everything later, but I want to point out a couple of important points about it, or a couple of facts about them. We start off with, you see over here we have vertex, maximum and minimum point, we have axis of symmetry, we have domain, we have range, and then below we have y-intercept and reflected points. Now, some of these you've seen before. You've seen domain and range, you've seen y-intercept. They all pop up again here. But let's start with our vertex. Our vertex is going to be this point right there. The vertex is where the parabola changes from one direction to the other. So you can see here, we're going down, 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 hit this point, and now it's up, 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 up. Okay? The vertex is that point where the direction of your parabola changes. If we had one pointing down, which we'll get to in a minute, it's where the graph's going up, 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 and then starts going back down. The vertex is a very specific point, and you can find it by simply looking at it. In this case, our vertex is 0, 5. Now, not only is that point the vertex, but it's also something else. Okay, you notice our graph is going down and it comes back up. So our graph, unlike a line would go from one side to the other. This one doesn't go from one side to the other. It stops at some point and goes back to the other direction it came from. Okay, so every parabola has either a maximum point or a minimum point. So it either has a bottom point or a top point, depending on the direction it opens. This one's opening up, so it doesn't have a max, it has a minimum. This point, not only is it the vertex, but it's also the minimum point, meaning that's the lowest that this graph goes. Okay, the minimum point and the vertex, or the maximum point and the vertex, are going to be the same thing, 0, 5. And that's pretty simple. I mean, if it's opening down, you have a top point. If it's opening up, you have a bottom point. The next term we have up there is axis of symmetry. Now, this is a symmetrical shape, meaning it can be folded in half on itself. Well, everything that's symmetrical obviously can be folded in half. There's a line where you fold it. Okay, that's called the axis of symmetry. And here, it's quite obvious on this one, the axis of symmetry is going to be right here. It's going to be the y-axis. It's going to be where you could fold this over and these all would match up. They reflect off each other as well. Okay, the axis of symmetry can be found by x equals negative b over 2a. Now, notice it's x equals, not y equals. X equals because this is a vertical line. This in this case, the y-axis, but it's a vertical line. Vertical lines are written as x equals. If it were horizontal or anything else, it would be y equals. But a vertical line, remember, is x equals. And I showed you that the form of a quadratic equation was y equals ax squared plus bx plus c. Well, this particular parabola is formed by the equation y equals x squared plus 5. Okay, so using that, we don't have a b up here. We have a, which is 1. We have b, which is 0. This would be c. So we don't need it. We would end up having negative 0 over 1, which is 0. So we have x equals 0. Okay, that means that our vertex, or I'm sorry, our axis of symmetry is x equals 0. Now that you would use that particular formula if you're not looking at a graph. If you're looking at a graph, just find out where the vertex is. Imagine you folded it over, and you'd be fine. Now, the next two terms are domain and range. Domain is all the x values, range is all the y values. For parabolas, it's pretty simple to do. We'll start with domain. Look at the x values. On our graph, they're going from about right here to about right here. But really, this graph's going to keep going up and 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 up. And the x values are going to keep getting bigger and getting smaller, actually. They're never going to stop. So our domain is actually from negative infinity to infinity. Okay? So it goes from negative infinity all the way to positive infinity. So basically, it's infinity. Everything can be part of the domain. Our range is our y values. Our range here is a little bit different. Okay? We have points at 16. They go all the way down. But once they get to 5, they pretty much stop, don't they? They stop, and then they repeat. So they're going down, 8, 6, 5, 6, 7, 8, 9, 10, on back up. So we have, for this one, we have a range where our y's are always going to be greater than or equal to 5. And you can probably tell that you get that range by looking at your maximum minimum point or your vertex. Okay. Now, this equation also has a y-intercept. You can see it there. It's 0, 5. You'll see on the next two that we do that doesn't have to be the same as a vertex. But then the last thing, we have reflected points. Now, I want you to notice that here's our axis of symmetry at 9. If we follow that out, that's 1, 2 points here. It's 1, 2 points there. They reflect each other. Okay, so if you know 1, if you know this point and this point and this point and on, you can also know these points over here. So we have reflected points. You're always going to have reflected points. Let's look at the next example. In this one, I'll go through these quickly. We have a vertex of 0, 2. We have, which is also going to be our max min point. We have an axis of symmetry right here. So again, it's x equals 0. We have a domain, which is negative infinity to infinity. We have a range that is y is less than this point. Since we have a maximum point, y is less than or equal to 2. Our y-intercept, again, is also 0, 2. And you can see points that are reflected here and here, here and here, and so forth, here and here. Okay. Our next example, we have one. Now this time it's not right on the y-axis, so it's a little bit different. We have a vertex which is going to be right there at 2, 6. That is also going to be our max min point. Our axis of symmetry is no longer 0, it's here. This is the line. That's at 2, okay? It's at x equals 2. Our domain, as always, negative infinity to infinity. And lastly, our range starts here and goes down. So y is less than or equal to 6. But now our y-intercept is different. Our y-intercept here is 0, 4. Okay, our y-intercept does not have to be the same as our max min point or our vertex. And then reflected points, you can see some here. We've got it here and here. We've got these two. Looks like probably these two. And obviously they're all reflected points, but you can see the ordered pairs here. Well, make sure you understand these terms. There's no work that you need to do before you come in, but you may go ahead and start working on it. Well, I guess you don't have your assignment. You can go ahead and start working on your practice and be ready to go when you come in to class. Thank you.